Okay, so today we're going to carry on with our discussion about limits. Last time we looked at the theoretical underpinnings of limits. Now we're going to focus more of our attention on a series of rules that we can use to calculate limits. And so we'll go back to the slides for a second and see where we left off. Let's, yes. So right about here, we were introduced to the idea that you can calculate limits by direct substitution in many cases. Now, of course, if direct substitution leads to a result like division by zero, then obviously you have to try something different. But in a lot of cases, calculating limits is a simple matter of substituting whatever value x is approaching into the function and coming up with your result. So here are some of the rules that we can use to help us deal with somewhat more complicated limits. And you can see, for example, if you have a scalar, you can simply factor it out of that limit. Here's an example of that. Let's say, for example, you're looking for the limit as x approaches 2 of, let's say, 5x to the third power. Now, you could substitute the 2 directly into x and you get your answer, and that would work just fine. But in some cases, when the limit is very complicated, it might be easier to move the constant on the outside of the limit, and that would mean doing this. Now, using direct substitution, we will get But of course, we could have just directly substituted in the first place. But like I said, sometimes when we have very complicated limits, it might make sense to move constants outside of the limit to just simplify what we're doing. What about these other rules? This one, the second rule is telling us that we can add the limit of a sum of functions is equal to the sum of the individual limits. So that let's say you had a case like this. Okay, so let's say this is our limit. Now what you can do, if it's more convenient, you can break it up into the sum of 3 individual limits. Here, let's say you can do this. Now, of course, it's very important to note that in each case, we're assuming that x is converging to the same constant, which in this case is 3. It has to be the same, otherwise the rules don't apply. Then what we could do is simplify it even further if we wanted to. For example, we could write this as for limit x approaches 3 of x squared plus 2 limit x approaches 3 of x. And then here we have the limit of 1 as x approaches 3. Now, the last one is very simple. The limit of a constant is equal to that constant. Here, in the first 2 cases, then we can use direct substitution. We've got 4 times 9, which is 36, plus 6 plus 1, which gives us a final result of 43. Okay, so yeah, we did mention that last time. The limit of a constant. Yeah, we saw a couple of cases here, or this case at least. The limit of a constant, it doesn't matter what x is approaching. The limit of that constant is equal to that constant. Okay, but for the other cases, you notice that we were using direct substitution. And yes, direct substitution, but again, this is fine as long as it doesn't lead us to a result like division by zero. What else do we have here? Oh, we've got the sum, and we also have differences. Differences work the same way. If I had differences, I could break up the limit into individual limits and then subtract them, and I'd get the correct result. For the product, I can multiply them together. For example, if I had, let's see, the limit of x goes to 0. Now, what I could do is multiply those two terms together and come up with a polynomial and then solve it with direct substitution. In fact, why don't we try that just to see how it works out? We have multiply these together. We can use the FOIL method. Sorry, we're going. This is not this. All right, let me try that again. If we're going to use FOIL, let's write it like this. That's better. So FOIL F means these two terms x squared. O is these two terms -4x. There's I, the two inner terms, and then last are these two terms -8. And that means x squared times 2x is 8. So basically, then I can rewrite this as the limit as x approaches 0 of x squared minus 2x minus 8. And then I can either substitute 0 directly into this expression or else split it up into three individual limits. Either way, I'll get the same result. So in this case, let's just do direct substitution. Not that again. When you're doing the actual calculations, you don't need the limit notation. So it's 0 squared minus 2 times 0 minus 8. So what about the approach we mentioned earlier where you multiply two limits? What would we get if we worked it that way? Copy this. And so, in other words, what we could have done is this. And now we can use direct substitution. And of course, we get the same answer. Now, there are going to be some cases where if these two terms are extremely complicated, it may be easier for us to solve for it by splitting it up into a product of two individual limits. It depends on the problem that we're working on. Sometimes it doesn't make any real difference. We'll get the same answer with about the same amount of calculations. But it's good to know that we can do this. And then, of course, the same thing holds for division, as long as we don't end up with division by 0. So if I were to take instead something like this, I could solve for it with direct substitution. Or I could rewrite it as the limit of x plus 2 over the limit of x minus 4. In both cases, as x approaches 0. Of course, get the same thing. Beautiful. All right. So those are the basic formulas or properties I guess we should know about limits. And now, of course, it's going to get more complicated than this as we go along. But for these very simple cases, especially when we're dealing with polynomials, these are very important properties for us to use because they can make things a little bit easier for us. Now here, they're going to give us another example of what we were just doing. The limit as x approaches 2. Of 4x squared plus 3. And what they're doing here is they are in fact breaking it up into the sum of two separate limits. So with direct substitution, we'll have 4 times 2 squared plus 1. Over here, remember, this is the limit of a constant, so we don't have to do anything. It's just equal to 3. Oh, wait a minute. What happened here? Where did I get this one? No, it's just 4x squared plus 3. I don't know what happened there. Um, it's 4 times 2 squared plus 3. We end up with 19. Okay, great. Okay. So what's coming next? Oh, by the way, this is an interesting graph. If you take a look at this, this is the limit that we just calculated. If you notice, the limit was 19. As x approaches 2, the limit of this function is 19. Now, because this curve is smooth and continuous, at least at the point that where the limit is, you notice how the limit is nothing but the function evaluated at x equals 2. Okay, in other words, this is what we mean by direct substitution. The limit as x approaches 2 of this function is equal to f of 2, which is partly equal to 9. Okay. So it's only when we have more complicated cases where we have discontinuities and that type of thing where this might not necessarily be true. Okay, most of the time, for a well-behaved function, the limit as we approach a specific value of f of x is equal to the function evaluated at that point. Here's another one. Now, this one could have been a problem. You notice we have a ratio and we have x plus 1 in the denominator. Now, that tells me that if we tried to calculate the limit as x approaches -1, well, that would have been a problem because we would have had a division by 0 with direct substitution. But fortunately, it didn't work out that way. We're being asked to evaluate this limit as x approaches 1. And there's nothing to stop us from solving this with direct substitution. As you can see, if I plug in 1 here, we'll get 1 squared plus 1 plus 2 all over 1 plus 1. And that reduces very nicely to 2, or f of 1. Okay, so we're lucky with this one, but later on we won't be so lucky. We're going to find ourselves running into situations with division by 0, and we'll see techniques for what to do about it. Now here, they're telling us if we're taking a root where n is restricted to being a positive integer, so in other words, this is either a square root or a cube root or a fourth root or whatever, then we can use the direct substitution method without having to worry about division by 0. So if you had, for example, the limit as x approaches c of let's say, just to give you a specific example, let's say that x is approaching 8, n is 3. Let's try that again. Yeah, it's being stubborn with me. You see how it won't let me get out of that eraser mode? It happens sometimes. So I'm going to just use direct substitution. And I just end up with 2. Now, what if we're taking the limit of a composite function? Let me show you a quick example of this. Well, again, unless we run into a problem like division by 0, we can solve this normally with direct substitution. Okay, so here we have the case of limit as x approaches 3 of the cube root of 2x squared minus 10. Okay, so direct substitution would give us the following result. All right, so we have 2, but they would like us to notice here that you see what they've done here, just as an alternative approach, they're taking the limit of just the 2x squared minus 10, and they're solving for 8, and they're getting 8. And then they're plugging it back into the original expression. Um, so it's a cube root of 8. So it amounts to the same thing, but where they're basically showing you is that um, when you have a composite function like this, we can just do direct substitution. Now, of course, we always have to deal with trig functions. You should never forget the trig functions. They're always hiding in the background somewhere. So eventually you knew this was coming. You had to calculate the limits of trig functions. So here they're being very helpful with us, keeping them all on the same page. And you can see it's literally nothing but um, direct substitution. That's all there is to it. All right, so we start with this one. So the limit of the tangent of x as x approaches 0 with direct substitution gives us the tangent of 0. And if you want to get that out of your calculator, so you didn't have to know off the top of your head that the tangent of 0 is 0, you can easily calculate it from the TI-84, and you'll see that it is 0. Now, here's an interesting one. This is one of those cases where trying to take the limit directly of x times the cosine of x. I guess in this case it would have worked if you just did direct substitution, but it might be a little quicker and easier to break it up into a product like this. It's not necessary, but if it's convenient, you can feel free to do it. So in the limit as x approaches pi of x cosine x and again, we can just do direct substitution here. And it turns out that the cosine of pi, now, by the way, if you're going to do this with your calculator, don't forget, you have to be in radians mode. So you go to the mode button and come down to the fourth row, although I'm pretty sure you won't be able to see that. The fourth row, if you notice, it says radian degree. If the radian is not highlighted, you have to go over there with your arrow key, hit the enter button, and then you're all set. Okay, so then you go back to cosine. Now, how to get to the pi key? I'll make a little note here. Second, caret, the symbol is called caret, by the way. It's used for exponentiation on the calculator and in Excel. So you would type second, go to cosine, then you would have second caret, close the parentheses, and it comes back with -1. Okay. Oops. That takes care of it. And then finally, we have the limit of the sine squared of x. As x approaches 0. So I think what they want you to do here is note that this could be rewritten as all right. And so now if you go to your calculator, the sine of 0 is 0. Well, that was easy. All right. Either that or direct substitution, you'd have 0 squared and you'd have 0. Okay, great. Now, the strategy for finding limits. So imagine a situation where you have two functions that are identical in every way except for a single point. Okay, so let's go with y equals x squared Actually, let me call this f of x. We can tell them apart. F of x is x squared. Now, g of x is a little bit different because what I'm going to do is this. So this one will be defined as a piecewise function. You may remember these from pre-calc, where you basically have two separate functions. So in other words, it's the same thing as the one on the left, except for that one point when x equals 2. In this particular case, the function is 1 instead of 4. So f of x and g of x are identical everywhere except at that one point. Then what they're telling us is that the two limits are the same at that point. Okay, whatever that point is. That the limit of f of x as x approaches 2 equals the limit of g of x as x approaches 2. And in both cases, 7 of 2 is 4. That means the answer here is 4. Okay, so now you might say, well, why is this how is this helping us? Well, because you might have a function that has a slightly strange behavior, and you might be able to lean on another function, which is very similar, to find the limit with the easier or simpler function than the one you actually have to deal with. It could happen. Okay, so if you ran into this case on the right, you might be confused about what to do, but then you might say, well, you know what, let's turn our attention to this f of x, which is identical except at that one point, and we can then go ahead and solve for it directly from f of x. You never know when that might be helpful. So here's an example they're using. Now, this one is interesting because the way it's written, and I mentioned this earlier, division by 0 leads to problems. In this case, they're going to solve for it in a very interesting way. If you notice, let's copy this one because it's a very helpful example. And you can see the problem here, direct substitution leads to division by 0. In fact, 0 over 0. Okay, so obviously that's a problem. So what they're telling us is, here's what we can do. We can cancel, we can factor. And if you do the long division, Let me just quickly run through this. So in other words, what this is showing us is that x cubed minus 1 over x minus 1 equals x squared plus x plus 1. Okay, so if you want, you can think of this as f of x, and you can think of this as g of x. Because what's going to happen is with f of x, which by the way, let's take a look at symbol lab for a second to make sure we're solving this directly, or correctly, I should say. Okay, so here's what we're after. This graph. Now, I'm not sure if symbol lab is capable of showing the function with a single point. I think it does have that capability. I'll tell you what I'm going to do. Let me see if I can get both of them. And the thing is, SimLab is very powerful, but I don't find it to be terribly user friendly in the sense that it's not obvious without going to Google how to do certain things in SimLab because their own instructions are absolutely awful. That's been my experience. That's often the case. You probably noticed that. Like with Microsoft, anything that Microsoft makes, their own help files are just ridiculously bad. And so if you really want to know how to use it, you really have to go to Google. So this is, let's think of this as g of x. And then let's go back to the original function. Call that one f of x. And let's show them side by side. I think this will work. X cubed minus 1 over x minus 1. There you go. This is where I wanted to see. See that there's the little hole where x equals 1. Okay, so let's copy this. There, yes, and you can actually see them side by side, although they're not scaled perfectly. But, oh, just had it. All right, maybe this time it'll actually stay. Okay, so that means here we have f of x, the original function. So anyway, you know what I just realized? It actually switched the two of them, didn't it? While I was moving them around. All right, well then this is the one, this is g of x, this is f of x. Fine. All right. So the questionable point is is one. Okay. So in other words, if I take the limit as x approaches one with the original f of x, I'll get 0/0. If I plug it in over here on the right, I'll get 3. Okay. Okay. So here's what they're trying to get at. Um, because they're only different by 1 point, left-hand side, in spite of that whole error, they both equal 3. All right, that's what all of that was all about. Okay, so you might look at it and say, well, there's a discontinuity there. Fine. It doesn't matter because this function on the right, it's the same function except for that 1 point. And in this function, g of x, the limit is 3, which means the limit of f of x at that same point must also be 3. Okay, so that's what they're getting at here. Okay. And so, yes, they put them together. So you can see they agree at all but 1 point, which implies this limit is the same as this, which in turn is f of 3. Sorry, f of 1. I'm sorry, I shouldn't have said that. It's g of 1 because that's the one that's defined there. Um, so while over here f of 1 does not exist, it doesn't matter because g of 1 does, and it's equal to 3. Okay. Beautiful. So here's what they're saying. Based on what we know so far, all the cases we've seen, in the vast majority of them, direct substitution will work just fine. If not, if it leads to a problem like division by 0, one possibility is to find another function that's identical in every way except that 1 point and see what its limit is at that same point, which is what we just did. Okay. Now, if that isn't possible, then you have to try something else. Now, based on the logic of what we just did, um, you know, this one, for example, you can clearly see if you substitute a -3 for the denominator, you'll get division by 0. So what you have to do is use long division, just like we did before. Let's try that. So we'll start with this case. This will be our f of x. The limit is x approaching. I'll just copy this. There. Okay. So let's do some long division. X subtract this one, we subtract this one, bring this down. And now if I multiply this by -2, subtract, they both become positive. Beautiful. So that means this expression equals okay. So think of this as our f of x. This can be thought of as our g of x. The two will be identical everywhere except where x equals -3. So therefore, the limit of the original function, x squared plus x minus 6, or x minus x plus rather, must be equal to the limit as x approaches -3 of x minus 2. And we ultimately end up with -5. So I guess I'm not going to go through the trouble of copying the graphs again, but you can see that they're identical to each other except at that one point, -3. In fact, they probably have the graphs in here anyway. Let's take a look. Well, they have the answer. Oh, no, there it is. Okay. So in other words, you can see there's a hole in the original function when x equals -3, but the new function lets us find the limit by using the approach that we just used. Now, we did run into this a few minutes ago. What if we have a ratio? It's bad enough to get division by 0, but what if we get 0/0? Well, that's bad news in calculus because, in fact, it gets its own special name. It's called the indeterminate form. And when that happens, we can't solve for the limit. So we have to try another technique. Okay, so what do we do about it? Well, there's several possibilities. We're going to see more of these as we go along. And some of these you'll see in Calc 2. But for now, we're going to look at this one. And you can see substitution, direct substitution would give us division by 0. We can't have that. So in fact, like I said, this is even worse because it leads to 0/0. No, we do not want that. By the way, there's other forms that are to be avoided as well, but we'll get to those later on. But 0/0 is one of them. Hey, what do we do about it? All right, well, there's a few possibilities. Now, basically, what you're going to try to do is rearrange this function algebraically to make sure that at the very least, you don't have 0 in the denominator, if you can do it. So here's what they're going to have you do. We're going to use a process called rationalizing, where what we're doing is we're taking whatever's in the numerator in this case. In fact, let's see how this works. You notice what's happening here. We're taking the numerator and instead of having radical x plus 1 minus 1, we're multiplying it by the ratio of radical x plus 1 plus 1 over radical x plus 1 plus 1. Now, what is this going to accomplish? It's a very good question. Let's find out. Now, in the numerator, we can do this in a couple of ways. We can use FOIL, or you can do something like this. Now, I've found that when I set it up like this, a lot of people don't recognize what is this approach that you're doing. Well, I don't know. It works. I mean, I'm not sure if there's a name for it, but what you're doing is you're basically multiplying all of the terms. We start in the far left corner, far right corner. So basically, all you're doing is multiplying all of them together. There's four multiplications that you need to do. The last one is you're multiplying radical x plus 1 times itself. You're just going to wind up with x plus 1. So copy these down. Now, these drop out. So that means the numerator is x. So what's going on in the denominator? Well, this is the easier one. X times radical x plus 1 plus 1. X times radical x plus 1 plus 1. Here you're just using the distributive property. Fine. So we come back up here and we rewrite that as x radical x plus 1 plus x. All right, so now what do we do? Well, now we have the opportunity to reduce it a little bit. Oh, there we go. Sometimes it lets me copy things and sometimes it doesn't. But anyway, let me copy this. Yeah. All right. Sometimes it's okay with that. Sometimes it's not. All right, x radical x plus 1 plus x. So there's clearly a common term of x in all three terms, the one in the numerator and the two in the denominator. So let's do this. So that's equivalent to the original expression we had. Okay, if you remember from all the way back then, that was radical x plus 1 minus 1 over x equals what we just came up with here. Now, when we try to take the limit, as x goes to, or approaches 0 rather, well, maybe this time we'll be able to do it with direct substitution. Looks like we got lucky. Or no, we didn't get lucky. We knew what we were doing. So we also end up with 1/2. So now if you notice, this function, the way it's written, direct substitution leads to 0 over 0, the so-called indeterminate form. But by using our cleverness, by rearranging it algebraically, we turn it into a form where direct substitution actually works. Wow. So we ended up with a correct answer, which is 1/2. Now, of course, you wouldn't know how to do this unless you had a lot of practice. So when you see radicals like this, sums or differences of radicals, this is something you should consider doing if you do need or end up with the indeterminate form. In mind an expression we can solve for it directly. I mean, not, but it's worth giving it a shot. Okay, so if you try something that doesn't work, try something else. It's possible that maybe you chose the wrong type of multiplication, but you can see in this case, by rationalizing this ratio, we ended up with the correct answer. I'm sorry, rationalizing the numerator. Now, by the way, the word rationalize simply means you're getting rid of the irrational numbers, which the radical x plus 1 could be, depending on what its value is, could be irrational. Now, of course, there's another possibility too. We can go back to our old friend, the tables, but I don't think anyone wants to do that. But yes, of course, if you plug these numbers in, you'll see the pattern that's developing, no matter which direction we're coming from, left or right, we're going to end up with 1/2. Now, while we're at it, why don't we look at this function in similar. I think it's going to be difficult to visualize what it looks like. All right, so let's go into Symbolab and let's see what they've got for us. So it was there it is. Radical x plus one. But Symbolab does have limits, although it starts out by assuming you mean as x approaches infinity. That's easy to fix. You just change type over it. Got to be a little bit careful with the radicals. You have to make sure you're outside of the radical when you go on to the next term with the arrow keys, that is. Oh, actually, I just realized I didn't mean for it to I'll ask it to calculate that anyway. I actually just wanted the graph. So let me, oh, what do you do? It's still giving me the graph. Oh, here we go. And that's a weird looking function. And if you notice where we were looking, there is a discontinuity. Okay, which means the approach we just used let us solve for it directly. In fact, I'll tell you what, let's do this. Let's take that function that we just created when we rationalize the numerator and see what its graph looks like. 1 over radical x plus 1 plus 1 thinking that's never a good. Oh, here we go. Yeah, see, exactly. So in other words, the one we started out with and the one that we created ourselves by rationalizing the numerator could be thought of as two separate functions, each of which is identical everywhere except at x equals 0. And so that's, again, proof that the limit must be 1/2. Okay. So in other words, when you do rearrange it algebraically, what you're basically doing is creating a new function where it doesn't have that discontinuity. So they're equal to each other everywhere except at that one point. All right. Now, this is a very theoretical result. Squeeze theorem. Um, it basically says that imagine as you can, I know the graph is a little small here. Let me bring it down here so you can see it better. So basically, you've got these two functions that act as boundaries to f of x. No matter what's happening, no matter what x is, um, g of x is always on top, h of x is always in the bottom, f of x is always somewhere in the middle, except at this one point c, where they all coincide with each other. And basically what the squeeze theorem is saying is that if the limits of h and g of x match each other at that point, then the same must be true of f of x. Okay. That's the only point where this is true. In other words, since c is the only point where then we have the same result. Okay. Um, you write this out just a little bit more formally. So in other words, and what's the point of this is that if you have a function f of x where it's going to be difficult to solve directly for the limit, if there are two other functions with this property that they coincide at that one point, but the relationship between them is everywhere else, then you could use their limits to come up with the limit for f of x. So again, it's a way of finding a limit based on the limit of another function. Okay. And sometimes this is the only option that we have. That's why it's important to know about this. And we'll run into some of these as well, of course. Let's see how many examples they have. Well, all right, let's try this one. Limit x goes to 0 of sine x over x equals 1. Let's see. Now, direct substitution is going to get us into trouble. Because if you remember from before, the sine of 0 is just 0. Now, we might be able to rearrange this algebraically to avoid this problem, but I can't think of any way to do it off the top of my head. But the reason why this works is because then you would have to be able to draw these out to see what's going on here. If you were to take, actually, I don't know if I can do this in Symbolab. I've always had trouble getting it to give me multiple graphs. They didn't actually prove these, they just showed them to us. I think they want us to work on this one instead. The limit. Now the tangent, now the good thing about the tangent is that we can rewrite it if we need to. As the sine of the cosine. Okay, now the sine of 0, let me just confirm this in the old calculator. Sine of 0 is 0. But the cosine of 0 is not 0. I don't think it's 1. That's what I thought. Okay. So direct substitution leaves us with 0. Okay. But they're asking us to do not the tangent, but the tangent over x. Okay. So in other words, tangent of 0 is 0. And so is x. Indeterminate form, what do we do? Well, what they're recommending we do is rewrite it as, okay. So we're going to use a little algebra, but of course, this is based on the assumption we already know that previous result. If you rewrite it as divided by x is the same as multiplying by 1 over x. So what you could do is rewrite it in a very interesting way. Now, a minute ago, they just got through showing us without proving it that this limit is one. So I'm not sure when they're going to prove this to us, but we'll take advantage of this knowledge. And now remember, the cosine of x of 0 is 1. So the limit of this tangent over x, tan x over x, actually works out to be 1. And so what we had to do, though, was take a trig function and break it up into a product of other trig functions where we already know what those limits are. So they've got the graph here. This is the function tangent x over x. And as we get close to 0, although this is not a good graph, it's hard for us to see where it's approaching 0, but okay. So now, by the way, there's another technique we could use to solve for this limit, but it involves something that we haven't seen yet. So maybe why they didn't bother to explain to us why the limit of the sine x over the x is equal to 1, because it requires knowledge that we don't have yet. So I will assume that that's what this is all about. And we'll see this fairly soon. But there's another technique we can use when we have an indeterminate form, but we don't know how to apply it just yet. So we'll have to wait until that time to prove that this actually equals 1. I think they just wanted to sneak it in there so that they can use it as an intermediate result, so that this part makes sense. I'm not sure if that was such a great idea, but anyway, so we're done here with section. Wait a minute. This is 1.3. So 1.4 is going to so what's going to happen here is we're going to review. Remember, we talked about how limits can be defined in terms of approaching from the left and approaching from the right. And that we're going to need that again in this section. Okay. So we're going to then develop more fully the concept of continuity. And so in other words, we're going to get a little bit more theoretical background here so that we can carry on and calculate limits of even more complicated situations. And yeah, you can see it's going to get a little intense here, but no, it won't be that bad. But yeah, well, we'll have to definitely save this for next time because we don't want to start something so complicated just yet. We'll hang on to this until next time. All right, so I'll see you soon.